are discussing about the different techniques for solving recurrence relations. In the last lecture, we have learned that how we can solve the linear homogeneous recurrence relation with constant coefficients, and also the simple technique of applying iteration, how we can get the explicit formula of the recurrence relation, that means the solution of recurrence relation. Today again we will read the how to solve the recurrence relation, that linear homogeneous recurrence relation with constant coefficient, but when the roots are equal, because last lecture we have seen when the roots are not equal. So, we will continue the solving recurrence relations. And we will see today how we can solve the linear homogeneous recurrence relations with constant coefficients when the roots are equal. So, first we read the theorem. So, let n equal to C1 a n minus 1 plus C2 a n minus 2 is second order linear homogeneous recurrence relation with constant coefficient yes C1 and C2 are the but here the roots are with equal roots. Roots are equal. Last lecture what we have done, that the roots are unequal. So, we can consider that the solution as if we consider that solution is of type V n equal to t to the power n. Okay. Then we get the equation as t square minus C1 t minus C2 equal to 0, and the root is, both the roots are equal to r, since the roots are equal. So, both the roots are equal to r. Then the solution is, then the solution is of the form is n equal to b r to the power n plus d n r to the power n, where n equal to 0, 1 like that. So, if we remember that when the roots are not equal, unequal roots, the solution is of the form b r to the power n d r to the power n. It is of the form this. Now, we will see that here if the roots are equal, it is n b r to the power n plus d n r to the power n. So, how we can first we prove that theorem. So, here mainly we have to show that if r to the power n, if r to the power n is a solution then n r to the power n, n r to the power n is also a solution. Okay. Now, since r is the only root, one root, since r is the only root and the recurrence relation, the equation is a second order recurrence relation and it is a second order recurrence relation. So, we can write that t square minus C 1 t minus C 2 equal to t minus r whole square, because both the roots are equal to t square minus 2 r t plus r square. So, this I give equation 1. One thing we write here, since last theorem we have seen that this t is coming from the, that as if the solution is V n equal to t to the power n is of this form. Okay. Now, from equation 1, what we see from equation 1, that C 1 equal to 2 r, C 1 equal to 2 r and C 2 equal to minus r square. If we equate the coefficients of the left hand side and the right hand side of the equation. Now, we have to show that if r to the power n is a solution, then n r to the power n is also a solution. So, we take that one solution with C 1 C 2 as the coefficient, that C 1 n minus 1 r to the power n minus 1 plus C 2 n minus 2 r to the power n minus 2, this is equal to, we put the values of C 1 and C 2. So, this is equal to 2 r n minus 1 r to the power n minus 1 plus C 2 is minus r square. So, minus r square into n minus 2 into r to the power n minus 2 . So, this becomes r to the power n into 2 into n minus 1 minus, here also r to the power n into n minus 2. So, if I take r to the power n common, then 2n minus 2 minus n plus 2. So, I get n r to the power n. So, if I take the same convention, that my solution u n equal to b r to the power n plus d n r to the power n. These are b and d are two constants, or two constants. And we can take that u 0 equal to some c 0 dash and u 1 equal to some c 1 dash, that type of constant. So, what we prove that n r to the power n is a solution. So, if we see the theorem, that this is a second order linear homogeneous recurrence relation with constant coefficients, while with equal roots, then we get that n r to the power n is a, or I give the solution as u n equal to b r to the power n plus d n r to the power n. Now, first we see one example. We see one example. We take find the solution of the following recurrence relation. Relation is d n equal to 4 into d n minus 1 minus d n minus 2. Coefficients given d 0 equal to 1 and d 1 equal to 1. Now, if we take, since it is linear homogeneous recurrence relation of second order, we can consider the solution is of the form V n equal to t to the power n. So, we get that t square minus 40 plus 4 equal to 0. So, t minus 2 whole square equal to 0. So, I get t equal to 2. So, here both the roots are equal. So, my solution is of the form. So, I get, if it is, we take the convention because t equal to 2. So, my S n equal to, I can take S n equal to 2 to the power n and T n equal to n 2 to the power n, n 2 to the power n from the previous theorem. Just now the theorem we discussed. So, my solution becomes u equal to b S n plus d T n equal to b 2 to the power n plus d n 2 to the power n. Now, we put the d 0 equal to 1, the condition we put d 0 equal to 1 and d 1 equal to 1 in this equation 1. So, putting the initial conditions d0 equal to 1 in equation 1, or d0 equal to 1 and d1 equal to 1 in equation 1, we get b 2 to the power n dn 2 to the power n. So, we get b into 2 to the power 0 plus d into 0 into 2 to the power 0 equal to 1, where n equal to 0, d 0 equal to 1. So, I get b, this becomes 0. So, b equal to 1. Now, if I put d 1 equal to 1, then b 2 to the power 1 plus d 1 2 to the power 1 equal to 1. That means, I put n equal to 1 and d 1 equal to 1. So, this becomes 2 b plus 2 d equal to 1. Already we got b equal to 1, b equal to 1. So, 2 d equal to 1 minus 2 b equal to minus 1. So, d equal to minus half. So, I get the solution, that my solution is d n equal to, I get the solution d n equal to b 2 to the power n, b 2 to the power n plus d n 2 to the power n equal to 2 to the power n minus half n 2 to the power n equal to 2 to the power n minus n 2 to the power n minus 1. So, this is my solution of the given recurrence relation. This is the my answer. Now, in the theorem we have considered the second order, we have taken the second order equation. So, if we increase the order, that means in general form, if we take the solution of k order. So, the general form that is the solution of linear homogeneous recurrence relation of order k with constant coefficient and when the roots are and the roots of multiplicity m. So, for second order equation we have seen that both the roots are r. So, I can take the value, now I can write that my equation becomes t to the power k, because it is of order k, minus C 1 t to the power k minus 1 minus C 2 t to the power k minus 2 minus C k equal to 0. And we will be getting the roots are, or the roots or roots of multiplicity m, or r is the, I write the r is the roots of multiplicity m. Then the solutions are r to the power n, r to the power n, square r to the power n in this way of multiplicity m. So, I get n to the power m minus 1 r to the power n. So, for second order recurrence relation, we have already seen the solution is n equal to b r to the power n plus d n r to the power n. Similarly, for third order will be getting that n equal to b r to the power n plus d n square r to the power n, like that, and we can continue when the order will increase. So, this is the general form we get. Now, so we have read the two type of solution techniques, that mainly for solving recurrence relation, linear homogeneous recurrence relation with constant coefficients when the roots are equal or the roots are not equal. Now, we see that some linear homogeneous recurrence relation, earlier we have seen that the how to frame the recurrence relation or as a recursive function also. Now, we see that how we can solve those recurrence relation. So, one such equation is our Fibonacci sequence. So, we know that, so I take the example, I take this as an example of solving linear homogeneous recurrence relation. So, this is relation is for, so solving recurrence relation for Fibonacci sequence. Okay. So, we know the sequence is f n equal to f n minus 1 plus f n minus 2, and for n greater than equal to 3, I write f 1 equal to 1, f 2 equal to 1. So, if I put that the equation or the solution is of form b n equal to t to the power n, we get, first I take f n minus 1 minus f n minus 2 equal to 0. So, I get t square minus t minus 1 equal to 0. So, if I put minus b plus minus root over b square minus 4 ac by 2a, so this t becomes 1 plus minus b square minus 4 ac becomes 5 divided by 2, 2 into 1. So, t equal to 1 plus minus root 5 by 2. So, I can write the solution f n equal to, I know that b s n plus d t n, and here I can write s n equal to 1 plus root 5 by 2 and t n equal to 1 minus root 5 by 2. So, this becomes this is equal to b 1 plus root 5 by 2 plus d 1 minus root 5 by 2. Now, if I put the initial conditions f 1 equal to 1 and f 2 equal to 1. So, first I put the initial condition f 1 equal to 1 and f 2 equal to 1, we get b into 1 plus root 5 by 2 plus d into 1 minus root 5 by 2 equal to 1, when putting f 1 equal to 1, that means n equal to 1, and b into 1 plus root 5 by 2 square plus n equal to 2. So, 1 minus root 5 by 2 whole square equal to 1, that means I put f 2 equal to 1, that means n equal to 2. So, if I solve these two equations, so solving we get b equal to 1 by root 5 and d equal to minus 1 by root 5, solving the above two equations. So, I can write f n equal to 1 by root 5 1 plus root 5 by 2 to the power n minus 1 by root 5 1 minus root 5 by 2 to the power n. So, this is my solution. So, this is my solution or the explicit formula for solution or the explicit formula for Fibonacci numbers. We can write Fibonacci sequence or Fibonacci number, that is Fibonacci numbers. Okay, this becomes Sn is 1 plus root 5 by 2 to the power, this is n 1 minus root 5 to the power n. Okay. So, we have seen that theorems that how to solve the linear homogeneous recurrence relation when both roots are equal or the roots are different, when we have considered second order recurrence relation, and we have seen some of the examples like the Fibonacci number, how to solve those sequences. So, next lecture we will see how we can solve the non-linear or linear non-homogeneous recurrence relation.